Super. Thank you. Okay, good afternoon, or good morning, good evening, good night, wherever you are. So today I want to talk about Zookeeper, and with this background, the paper that we was assigned for today, which is from 2010. So this is going to be, we're going back in the last couple lectures. I think we dove in quite a bit of detail into draft, including sort of looking at code. The lectures from now on are going to be more conceptual and exploring ideas in distributed systems through papers. And the Zookeeper one is particularly relevant to us because it has a little bit of a relationship, as we'll see, with Lab3. So it will allow us to talk about a little bit of some properties of Lab3, and particularly linearizability. But the Zookeeper system, more importantly, is interesting because, one, it's a widely used system in practice, well beyond Apache, well beyond Yahoo. There's an open source Apache project that is still active. And particularly what's interesting about it for us in this lecture today is actually high performance. And with a high performance, I mean much higher performance than what actually Lab3 is going to be. And we'll talk quite a bit of the detail about this. And there's sort of two reasons why it is high performance. One, the client operations are asynchronous. And really what high performance here means is that the system can process many more operations per second. So it's really a throughput metric. And the second reason it's high performance is because it doesn't provide strong consistency. So it doesn't, it has an interesting consistency definition. And it gives us some freedom to execute basically read operations on any replica, and therefore read conforms can scale. Then the second aspect that is interesting from Zookeeper is, in addition to being high performance, it is sort of a generic, what they call a coordination servers. And the point being here is that there are many applications where you need to sort of keep track of like who's part of this cluster and who is the master. So think about the MapReduce, or so think about the GFS, the master in GFS. It needs to keep track, or like for every chunk, who are the servers that actually serve the chunk, and from whom the service actually is the master. And so tracking that sort of configuration information, comes up in lots of different distributed applications. And Zookeeper is really designed, to support that kind of thing. So you can just sort of outsource all the configuration management to Zookeeper. And then focus the rest of your application development on other aspects of your distributed system. Okay, so that's sort of a brief introduction, and the topics that we're going to be talking about. And as usual, feel free to interrupt at any time, or post something in the chat message. Let me actually pull up the chat. Okay. Good. So just to just start from the basics, Zookeeper is a replicated state machine. In the same way that the replicated state machines that we've been seeing, and so let's just draw the usual picture. We have some service. In this case, it's going to be Zookeeper and ZK. It receives requests from clients, say create a Z node, and basically the way it interacts to distribute these operations, it has sort of a separate library. Think about this as the Raft library, but in their case it's called Zap. And basically, the leader sticks the operation into the equivalent of the Raft library that talks to other libraries on other peers. Then it basically creates a log that contains all these operations and all these machines And then the operations are of the log of feedback, to the through, so in our case, it would be the apply channel to the service. The service applies the operation in response to the client. And so we have basically a different version of this running. And so far, in the labs, we've been focusing mostly, lab 2 is all about, this part, implementing, in our case, Raft, so instead of Zap. And for the first order, at a very high level, you can think about Zap just being another Raft, providing sort of similar guarantees, although implemented quite differently. It provides an order of all the operations, despite failures, network partitions, et cetera, et cetera. It doesn't suffer from split brain, all the sort of things that we sort of associate with the Raft library. And what we're going to be focusing in lab 3 on is actually implementing a service on top of it. And so this paper talks about this coordination service, Zookeeper. We're going to actually implement in lab 3 a key value store. And the data structure is just a map, from keys to values. And so the operations that we're going to be supporting are, put and get. So the client submits put and get operations, to the service. The service runs them through a Raft, and then applies them one by one to the key value store. And in Zookeeper, the structures are slightly different. There's a tree of Z nodes, but the basic operation is the plan is the same. The lower layer, the lab or the Zap library or the Raft library orders all the operations. They're applied in the same order on all replicas. Because they're applied all in the same order, there's no non-determinism. The resulting state on each of the replicas is going to be identical. Okay, so that's sort of the basic setting of this paper, and sort of also the part of the relationship between lab 3 and the Zookeeper service itself. I'm mostly going to be talking in this lecture on focus on the Zookeeper part itself, and not talk about Zap, because this is going to assume that's sort of similar to what we're doing in lab 2. Okay, I want to talk a little bit about what kind of performance would you observe if you once you finish lab 3 and would measure how many put and gets you operation you get through per second. Because like one of the achievements of this paper is this high performance. So let's think a little bit about that. So let's assume there's a put operation coming in, and put operation comes in by the leader, and so we're just going to go for the normal case, like the standard case where everything is working, no network failures, no partitions, nothing. Everything works out perfectly. So here's the leader. We got 2 followers, and just by now that protocol probably inside out. The first thing, of course, that happens, like you would call the leader call start. The start actually writes the put operation to the log in the leader, and then the leader propagates its log to the other followers. And we saw before that actually happens in parallel. Let me draw this slightly differently. Basically, it launches a bunch of RPCs almost instantaneously to the different followers. Each follower, of course, will append the entry to its log, so that requires a write, to persistent storage. Same thing here, and then they respond back. And so here is the response back. And in this case, if a majority has responded, the leader can actually apply the operation. So the leader will actually apply the operation here. Sorry, let me not indicate it. So do the put and send the response back to the client. And so what we're curious about is like how many puts per second can we actually get, in this setting. And if we think about it, when you do gross, back of the envelope calculation, and we don't really care exactly about the exact numbers, but one round trip. We need at least one round trip to actually get the majority, right? The leader needs to talk to at least one follower to actually maintain the majority. So we're going to have at least one round trip of messaging. And then we sort of need to look at the writes to stable storage, because those tend to be expensive. And we'll see, in this case, we're going to have two writes. There's going to be one write at the leader, there's one write at the follower. At that point, we have at least two nodes that have a copy. So the thing will be committed if no further failures. And so basically, at minimum, we're going to need two writes. So that's sort of the base and the best you could do, right? At least in the sort of the simple scheme that we discussed here. And sort of we can think about like what the cost is. And in a round trip, maybe it was running in the data center network, so not across the internet. Maybe that actually comes down to 1 millisecond. We're roughly in the neighborhood of a millisecond, maybe a little bit faster, but we don't really care about it, as we'll see in a second. So we're going to do two writes to stable storage. And writes actually to stable storage tend to be expensive. And it depends, of course, like what medium or what technology you're using for stable storage. Let's assume like we're using SSDs, sort of pretty typical. And then, presumably one write is in the order of maybe 2 milliseconds. We got to really make sure actually that the write ends up in the SSD. So it probably has to be a synchronous write. So that means like 2 milliseconds for one write. So two writes would be roughly 4 milliseconds. So we add it up, that's going to be 5 milliseconds. And so how many operations per second? Just to see if anybody's still awake.
200.
Yeah, so that's going to be 200 puts per second. Any questions about this? Does that make sense? Okay. So now let's look at Zookeeper.
What's the round trip for in the writes? Sorry, I missed it.
The writes there's no round trip. There's one round trip, correct, to talk from the leader to the follower, and the two writes, one at the stable storage for the leader and one at the stable storage of the follower. And the two writes add up to 4, the round trip to roughly 1 millisecond, so the total is 5 milliseconds for one put. Okay, let's look at Zookeeper. And again, the metric that the paper is interested in is the throughput metric, where basically the clients, you have many clients, and they pump many requests to Zookeeper as much as possible, and pipeline them aggressively. And so let's see what the results of that is. And so let me pull up the graph out of the paper. And let's look at that paper a little, the graph a little bit. So a couple things presumably to observe. On the x-axis is the percentage of read requests. As we'll see in a second, this is going to be important to distinguish read from write operations. And so write operations are really operations that modify any write operation that modifies the state, and read operations are operations that don't modify the state at all. So in our in lab 3 terms, put would be in a write operation, and get would be a read operation. And on the y-axis is the number of operations per second. And let's look at the case of free servers. And so the first thing you notice is that at 0 reads, so only write operations, so the ones that modify the state, we get roughly 21,000 operations per second as throughput. All right. And we look at if the system only has reads, that actually gets a lot more. It gets up in the whatever the 60-70 region. And in fact, what really was going on is that the number of reads, or the throughput in terms of read, just scales with the number of servers. So if you have 3 servers, you get 3 times the read performance of 1 server. If you have 5 servers, you get the 5 times the read performance of 1 server. That's of course not true with writes, correct? Like in fact, if you look at this graph, you see that if with more servers, the write performance actually goes down. And the reason for that is presumably the leader has to chat with more servers to actually get this operation through. And so when we're purely doing write operations, we're actually limited, and we cannot expect more performance than a single server. And in fact, if we add servers, we're going to go down in performance. And so this 21,000 per second, even for a single write operations, with a configuration of 3 servers, is an impressive number. It's quite a bit higher than actually the simple sort of calculations that we did for lab 3. Lab 3 will never get will not get close in the neighborhood at all. And so we want to understand, we want to see in this design, what did the designers do to actually get that kind of performance. And so there are two, as I mentioned earlier, there's sort of 2 key ideas. One, everything is asynchronous, or the clients can submit many operations to Raft or Zookeeper, sorry, in a single shot. So they're all pipelines. So basically, when the way to think about it, the Zookeeper client basically says, please start executing this put, and doesn't wait on the response of the put. It just immediately issues the second put, and then the third, and the fourth, and the fifth. And so, for example, a lot of these puts run will be batched all together, maybe even in a single message, all be transferred to the leader, and the leader will apply them all at the same time. And in fact, the leader will write to the persistent storage only once, for this whole batch of operations. So instead of having one write per operation, you're going to have one disk write for many, many, many operations. And this is one reason, they get this, very good performance on write operations. And then the second thing is they do something special for read operations. They allow read operations to be processed by any server. So instead of running all the operations through the leader, they allow operations to actually be processed by any server. So, and then the latter, I want to talk a little bit more about it. And I think I want to just think about, could we do something similar? Like, let's say we want to do lab 3. And we're going to do the same trick. We want to look at the lab, basically reads from any machine or any peer, I guess it's there. So the picture would be as follows. We have a leader, we have the 2 followers. We just stick to the case of 3. We have a client, and we're going to consider what actually could happen if we sort of naively follow this strategy where we're going to read from anything. So here's our client. The leaders actually, when we do puts, they all go through the leader. And so the client, basically does a read. And let's say, this was a put was done. And at the same time, or roughly after the put was done, the client issues a get. And it talks to one of the followers, an arbitrary one. Let's say for this case, it does not talk to the leader. And then, we're the follower responds. And the question is, what value does the get observe? And so what's the possible values, that the get can observe? Now, let's say that, we're reading whatever, the key x, and that initial, the value of x is 0, and this put actually put x to 1. And what are the values that get can actually return if we don't do anything particularly special?
So just a question here about the setup. So if we're assuming that Raft is the infrastructure here and get is just another command, then wouldn't the follower just redirect the client to the leader to put the get request through the leader? Or
no. So the goal is correct. We're not. We could do that. There's a lot of things we could do, but we want to get this perfect scalability. So to get perfect scalability, the follower cannot talk to the leader for read operations. So basically, read operations are executed by the individual followers immediately without no communication, because that's the way we're going to get perfect scalability.
Oh, I see. So they're not even communicating with.
Yep. So I'm just doing the naive plan. Let's say our goal is to get perfect scalability, like Zookeeper does, and we want to understand is that difficult or easy, or what does that really mean? And so the first thought experiment is like we do absolutely nothing at the leaders, at the followers. The followers get the read operation, they execute it, and return the value.
Okay, awesome, thanks.
And what can so then the question is what values can be returned by the client observe in this picture?
Can be either, because maybe they didn't make it through the desk of the leader yet.
Yeah, so it could be either going to return 0 or it could return 1. Right? So it can return stale data. It's a possibility. Let's say we do the let's say it returns 1. So this get returns 1 used for a thought experiment, and then the client does another get. I'm not going to really say to where that get is going, but in what values could we see in response to that get?
Assuming there are no other writes, it should be a 1, right?
Yeah, unfortunately, because I have 3 servers. If I had 5 servers,
Why is it different?
okay, let's make it different. So certainly it can return 1, correct? That we're agree on that, because if the follower talks to the second get request, talks to a follower that actually has seen the put operation, which the majority of them has seen the put operation, we're going to get a 1 back, correct? And the real question is, could it see a 0? Even though it observed a 1 earlier.
I mean, it could see a 0 even in the case of 3 servers, right? Because let's say that you have the majority of servers.
Okay, let me do first the 5 case because it's simpler to see.
Are we assuming that the client always asks the same peer? Or
No, correct. There might be a little network partition or a disconnection for a brief period of time. So, it doesn't have to talk to the same peer as the last time, correct?
yeah, so in that case, it can talk to a different peer and that peer may respond with 0, and that's inconsistent.
Yeah, exactly. So this is possible. So, we're going to have this sort of strange behavior, correct, in this configuration where you might see a recent, in the first case, we might see actually a recent value, and then we read actually something from back, back in time. Yeah. So if we do nothing special and we just naively read from any peer, then we have sort of 2 types of problems. I mean, the get can return stale data, and the get can return data even from back in time. And so,
sorry, wasn't this possible also with 3 followers? Because the majority was the leader and 1 follower, and you could ask the other one.
If you've seen the 1 and yes, it could be possible. Absolutely. The 3 would be possible too. I think with 5 is just much more clear that this is possible. Okay, so then we're going to go back and sort of think about a little bit of this behavior, correct? The returning those values, is that okay? And this is sort of an interesting question, and it depends, of course, what you mean with correctness. And what if something is okay, it depends on what our correctness definition is. And the correctness definition that we've sort of been peddling for the last couple lectures, or since the beginning of the term, is this notion of linearizability. And roughly what that means, we talked a little bit about it in a week ago. It behaves like a sort of a single machine. That's the intuition that we've been using since the beginning of the semester. But the definition of linearizability is a little bit more precise and sort of tries to nail down what it means to behave like a single machine. And so when something behaves like a single machine, first of all, it has to be the case that even if the operations execute concurrently, you can sort of order them in a total order. So it's possible to construct a total order of all the operations, because in the end, it's a single machine. So if it behaves as a single machine, there's only one machine, sort of virtual machine, that can actually perform the operation. So a total order of ops. And there has to be some properties true about that total order. And so one property that has to be true is that the order matches real time. And with real time, really what I mean is that if an operation completed before another one started, then no, that first operation has to go before the second operation in the total order. And then there's a third property that the read operation, read op returns value of last write. And that's sort of the official definition of linearizability. And you can just think about this as sort of a more precise statement of this, first thing, this intuition, namely the whole thing behaves like a single machine. Now we want to go back and think a little bit about the scenarios that we here have just on this whiteboard, namely these two cases of stale data and back in time. And think about that. Think whether linearizability allows that. Right? And so, let's first focus on the first one. So we have a client one. Correct? If the way you would draw this out and reason about linearizability is you draw diagrams of this form, where the left bar is the start of the operation, the right bar is the acknowledgement to the client that the operation has to be executed. And in this case, we're sort of saying was a put to X, and that put the value 1. And then we had another client, or the same client. Well, let's draw another client that basically did a read, and the read started well past the put operation. So this was a get of X, and we had one case where the get of X actually returned to 0. Right, that was the first possibility. And so that's what actually happened on the previous board. And now we want to sort of think about this: is this execution allowed by linearizability? Right, this is the correctness definition that we're looking for. And we want to see if this execution, this order of operations that happened in practice, at least we have seen that it's possible in practice, is this allowed by linearizability? And that is our correctness criteria. And is this allowed by linearizability?
No.
No, why not?
Well, because the C2 client operation started after the C1 completed. So in the total order, you have to have put X1 and get X, and it should be 1 because it should read the last write.
Yeah. So basically, in the total order that you construct, this guy, this operation must be after that operation because it started later. But then you look, that violates rule number 3, correct? That an operation returns the value of the last write. That's actually not the case. It actually returns the earlier value. So this is not linearizable. Does that make sense? And of course, this totally matches our intuition, right? Because this is in a single machine, this could not have happened. You wrote a value to the single machine, and then you read it back, and it's certainly another value. It's actually a previous value. So this is not allowed. Okay, let's do a second one, like our other example. So we had a client 1, again, it does the put. And I'm going to draw it a little bit more compact because I don't have much space. And we do put, then we do, there's the read or the get. The get returns 1. So we're not in the first case, but in the second, and we're in another case. And then we have a get that returns 0. And so that's the second sort of case that we looked at, correct, at this picture, the back in time case. And again, we can ask ourselves the same question. Is this allowed by linearizability?
No, because the read wouldn't be returning the value of the last write.
Yeah, it's a pretty straightforward observation, correct? This is absolutely not the case. In fact, it's almost simpler in the first case because, even these operations have to be in this order, but that could not have happened when that would violate rule 3, correct? Okay, good. So this gives you an intuition of what linearizability means, how you reason about it, and basically, if we don't do anything special and we do this naive scheme. If you were implementing lab 3 and you followed this naive scheme, then you would not pass the test because the test assume, or our goal in lab 3 is actually to provide linearizability for putting gets. And so the scenarios like these ones are just not allowed. Your implementation has to be in a way that these results cannot appear. Does that make sense? So we're going to, in lab 3, we're going to shoot for linearizability. And what is one easy way of getting linearizability? How are we going to ensure that put and gets operation are linearizable?
Well, I mean, if you do actually only use one machine, then it will be linearizable, right?
Yeah, so what is the easy solution? We run all the reads through the leader, correct? So basically, the easy solution to get linearizability, and in fact, that's what we're going to be doing in lab 3. In lab 3, what we're going to be doing is, reads or get operations, get ops, go through the log. So they go through Raft. And as you observe, it seems, if they really go all through one machine, well, it's not, they might not go through all one machine because the leader may change over time. But we know that the leader is always total ordered, correct? And that the log is total ordered. And so we're going to be able to construct, a total order that actually has, the order matches real time and all the reads to return the values at the last write. Because basically the Raft protocol will guarantee that all the entries in the log are in a total order. Right? And of course, the Raft protocol has to do quite a bit of work to actually make that all happen. But despite network failures, despite network splits, the Raft protocol will guarantee us that basically all the operations happen in a total order. In fact, the whole replicated state machine approaches are based on this idea, correct? That like all the ops in a total order and applied in the same order on all peers, and as a result, everything looks like a single machine. And so the easy way to solve this problem is to run all the reads through the leader, whoever the leader is at that particular point in time, and that will give us linearizability. Let me pause for a second here. Any questions about this?
Sorry, matches real time. It just means that if operation 1 ends before operation 2 starts, then 1 is before 2.
Yeah. That is Raft. You will see that this will happen automatically, correct? Because if an operation actually completely finishes, then must have been the case that the leader responded, back to a client, and then if the client started the operation later, it must end up later in the log at the leader. So this is going to be a property that's true.
And also, so just to double check and maybe reiterate, so in lab 3, all of the client requests are going to be synchronous. So
yes,
okay.
Absolutely. Okay, good. So one downside of this scheme, we would go back actually. If you read the Raft paper very carefully, there's an optimization for read-only operations. But even that optimization requires some communication. And so, like if we just follow this naive, so this straightforward plan to actually get linearizability, what does that mean for performance? We go back to sort of thinking about, contrasting it with Zookeeper. Is, for example, the number of read operations is going to scale with the number of servers?
No, because now everything has to pass through the leaders.
Yeah, everything has to go for the leader again. So no matter, it's a little bit undesirable, correct? And so, like, an interesting question is like, how is it possible that like the Zookeeper gets this great performance, and like we see that the simple scheme actually doesn't really work, or at least violates linearizability. And so so we want to talk a little bit and like to understand like how does Zookeeper get this? And so the first thing to really realize, and this is probably the most important part, is that Zookeeper does not provide linearizability. It basically changes the correctness definition. And so the Zookeeper service is not going to behave like a single machine. It's going to have results that would never happen on a single machine. And so what is it? What does it provide? Well, it does provide linearizable writes. So all the operations, all the write operations actually, go through the leader and, go through the log and are appended to the log every peer in the same order. And so they're going to also be applied in the same order. So we still have this replicated state machine approach, or where we apply all the write operation, all the operation to change data into in a total order. But there's a couple more properties. But it does not provide linearizability for reads. Instead, it sort of provides two sort of a different property, which is that all the operations appear in FIFO order, in FIFO client order. And this partially has to do with the asynchrony. A client may submit multiple requests one by one without waiting for a response. And Zookeeper will guarantee that if you submit, if client 1 submitted a request and then client 1 submitted another request, then that second request will appear later in the result. Will observe the result of the first operation. And so, in particular, writes go in client order. And then reads is where all the action is, where the interesting properties are. The reads observe last write. Okay, so reads reads observe last write from same client. And so this sort of makes sense. Basically this sort of says like you read your own writes. So if you did the write operation, you immediately follow the read operation, you see at least the results of your own writes. But for writes from other clients, the Zookeeper does not guarantee that property. Instead, what it guarantees is that the read will observe some prefix of the log. So this means, correct, that you can actually see stale data. Because you may, read from a follower, and that follower has a prefix of the log, but not like the last entries in the log, because maybe it just got lags behind a little bit. Nevertheless, that follower is allowed to return a value. Because the only thing that Zookeeper is going to guarantee is actually reads observe a prefix of the log. So the operations can now go out of order. Once they're in the log, you can't sort of reads can't like read operations out of the log in out of order. It really has to be a prefix of the log. And then there's a second requirement that you cannot do no reads from the past. And that really means like if you saw some prefix 1, and then you issue like a read saw prefix 1, and then you read a second read, then that second read has to see at least prefix 1 plus more. And it might be no, it might be just prefix 1, but it cannot go back in time. So it cannot see a shorter prefix than prefix 1. And so this basically, so if we look back at this picture, the Zookeeper will allow this in certain cases, namely if the two clients are different, but it won't allow this up. This you can never have back in time. Okay.
So I have a question, a conceptual one. So we have these two consistency guarantees, the linearizable writes and the FIFO client order. So if we ignore the second constraint for a second, and if we only focus on the first one, does the definition of linearizable writes actually make sense, since the definition of linearizability depends on having a read operation and a write operation? So it's
hold that thought for a second, because the way they define linearizable writes is that basically the writes are a total order, but there is a relationship between the reads and the writes. So hold that thought for a second, okay? We'll come back. We'll get to that in a minute, like in one board. I want to make one board in between, okay?
Sounds good.
Okay, so let's look a little bit at how Zookeeper actually provides these guarantees. And so to get the intuition, how you could implement this. The paper is actually not very explicit about how they implement this, and sort of like I'm going to give you sort of a roughly best guess. So there's a Zookeeper client that runs on the client machine. In Lab 3, we call this as a clerk. And so this is a piece of software library sort of that works, collaborates, with the service. And in the Zookeeper, in the paper terminology, basically it is the thing that has the session. So when you join, when a client wants to connect with the Zookeeper service, it creates a session and connects, using the session information to the leader and maintains, state across the session. So we have a leader in Zookeeper, as we'll see. We have followers. Basically, this is all sort of similar to what we are used to from Lab 2. And the Zookeeper client issues a write to the leader, because the writes are going to be linearizable. In fact, the writes basically follow exactly sort of roughly the same strategy as in the Raft library. So there's going to be a log, and in the log all the writes are entered. So whatever, there's some slots. Let's say the leader pens this write, in this particular index. So this, has an index, and in the paper they refer to this index as the ZXID. So I think you can think about the CXID basically as the index in the log. And when the leader, basically commits an entry, write, to the log, it returns the ZXID back, to the client. And so the client maintains that state. So associated with a session is basically, with CXIDs, the CXID of the last write. Okay. And so when the client later on does a read, and the read doesn't have to go to the leader, because that was the whole goal, to get more performance. So maybe the read actually will go to one of the followers, but the read will be tagged with the CXID of the last write that particular client has done. And so what does that mean? Well, let's say this follower is behind, correct? And it has 2 entries, but it hasn't actually observed the write yet, because whatever, the leader maybe committed it through the other follower. And what happens in this case is that this read, the follower won't really respond immediately. Instead, it will wait until it's seen the ZXID. And as soon as it's seen the ZXID, it actually will respond. Now, of course, there's going to be another client. And so maybe at some point, this write will come through. And maybe now the read, the client does another read. And so it hasn't seen no other ZXIDs. And maybe maybe make one more follower. Let's say there's yet another follower, and that actually has not observed, that final write yet. Or actually, so there's going to be another, let's say there's a other client that sticks in some other write. That's the scenario I want to talk about. So there was another client that actually appended a W after the CXE, it is right here, but it was not observed. That particular write, what we have here is we got the 2 slots, we got the write, but the green write hasn't really shown up at that particular follower. And so if the client now issues a second read, and maybe that goes to the other follower, it has the same ZXID because it hasn't seen any new, that client has not issued any new writes. It will arrive there, and that guy is allowed to respond immediately because it has seen the ZXID of it has seen the last ZXID of that particular client. Of course, it misses some writes that might from other clients that are already being processed by some majority of the servers, but it is not required to return that data, and so it can just return it. And so this might actually return then in stale values, but that is allowed by the definition of the Zookeeper correctness guarantees.
Professor, I have a question.
Yeah.
First, I thought I'm not sure, but I understood the client reads, like the session reads, were sticky. So they would like in general go to the same okay.
Yeah, but of course, there might be a little bit of, might be a quick network petition or anything like it, and so in between time, it might have switched to another server.
Okay, and then
In addition, it turns out the Zookeeper does actually do some load balancing. But nevertheless, it can happen, correct?
Right. The other thing was you said right. Always go to the leader.
Mm-hmm.
And then the leader responded with the ZXID. Doesn't the leader have to like first like reach consensus before responding, or in this?
Okay. Yes, I guess so. You just have to commit it because otherwise it's an uncommitted right. So I think the exact protocol. Okay, I'm abstracting away a little bit from the details of the protocol. I'm just going to sketch of how it works. I believe you're right. That it must return presumably after the entry X is really committed.
Then sorry, last thing. You said it always goes to the leader, but I think the paper described like it could go to like followers, or right could go to a follower and then be.
Yeah, but it then ends up at the leader, correct?
Mm-hmm.
So in the end, it goes for the leader.
Perfect. Thanks.
Yep.
Just to clarify, when you say wait for ZXID on, like, for example, the second follower or so second, when we wait for ZXID, we're actually waiting for it to be committed, right? It's not sufficient to just get.
It must be committed. Yeah.
Got it.
Wait, but what it would have been committed by the time it was like a client wouldn't get an uncommitted CXID, correct? Like ever? Like
no, yeah, but that's correct. So if this point, okay, at this point when the follower sees this ZXID and the write is in that particular CXID, it must have been committed because the client could have not have gotten that CXID unless that option of that ZXID was committed.
Thanks.
Also, so when you say that from the read you get stale data, so like the last basically arrow, but the client here in the read request, it supplied the ZXID within it. So it's as if the client knowingly exactly wanted that location in the log that had ZXID as its index.
Mm-hmm.
So didn't it knowingly just request that prefix, that specific prefix of the log?
No, but it really says, what this basically ZXD says, like, it basically counters, going back in time. And so the ZXD says, like, you have, as a follower, you have to return me a result that at least includes the prefix of the log through CXID. Oh, you might have more, that'd be fine too, but at least through CXID. And this just stops that one case where you're reading back in time.
Okay, awesome. Thanks.
Okay, so now you might wonder, so this clearly does not provide linearizability. And one reason people are excited about linearizability is because it behaves like a single machine, so it's easier to program, right? Like, you do a put, you get a get, you roughly know what you're going to get. And no pun intended. But here, you certainly have a model, programming model that's different from a single machine. And so, how do you program with this thing? And it turns out that basically these rules, this correctness definition that Zookeeper has, are basically, you can think of as like they're good enough to actually do for the purpose to help programming. And so I want to talk a little bit about that. So the real point is that with linearizability, it's pretty clear that that helps programming and writes so intuitive programs. Here things are going to be slightly different, and we want to understand actually if things that work out well, or whether it is like just pain in the neck to program and just basically completely unusable. So let's look at one of the key examples they talk about in the paper, and the first thing I want to do is like basically ignore the sync operation, because like you can make every operation actually linearizable by just issuing a sync, like before you do the read. But that, of course, makes everything very slow again, and we're not going to get our performance advantage. So basically, we want to avoid doing syncs, and so I'm just going to ignore syncs and like program as if we don't have syncs. So let's look at the following operations. So here's the write order. So we're going to do a couple operations, and this is the case of the ready file. So we issue a delete of the ready file. So for example, this is a new master that becomes the new leader, and so it needs to write the sort of configuration information in it, like who are part of the replicated state machine and who is the leader. And so it writes some configuration files. Write F1, write F2, and then does a create of ready. And then other followers might, this is the read order. They can, for example, call, if exists ready. And so Zookeeper has this operation exists, and if ready exists, then it will immediately return true, and otherwise not. And so you have to wait. So let's ignore that case for a second. Let's assume that the second client. So here is the one client did the write operations, second client does the read operations, and then if it exists, then the client reads F1 and then read F2. And so the thing that we want to understand, like what values could F1 this read actually return? And I think the thing that we worry about, correct, is it could return, could it return some result of a write that was done much earlier here? Or must it observe this write?
I think the paper mentions that the reader can watch certain things and be notified of changes.
Yeah, so let's assume that actually the file exists. So create actually succeeds immediately. So let's talk about the notifications in a second. So this exists, returns immediately. No watches involved, it just exists. And then we do that second client does a read of F1.
I think it should read whatever was written by the first client because the operations are in FIFO.
Yeah. Correct. So I think the real thing that actually so if we saw this option value, correct, like for some write earlier, that would mean that we're reading back in time, correct? And that is just not allowed. The rules actually forbid that. This read, must observe, this that value of that write because this read, the previous read, the exist, observed this write, correct? So we know that this exist ID must have seen the ZX ID corresponding by that create. And so that means that this read will must sort of see the last write that was performed in the total order that preceded that particular create. And so the last write in that critical order before that is this particular write, right? Because all the writes are actually linearizable. And so it must be the case that this read F1 observes the result of the write F1. And so this is nice, correct? Because if like some new leader became the primary, get raised to configuration file, we know for sure that actually we're going to see that last configuration file that was created by that new leader. So we see here an example that these rules are sort of carefully chosen, that things that you might care about if you're writing a configuration service that actually sort of they work out.
Wait, sorry, I might have not understood what you were saying before, but in this case, if it exists, like if it's checking exists ready, couldn't it read like stuff before ready was deleted?
Okay, all the writes are in total order. So this write is in total order, that write is in total order, the create is in total order, right?
Right.
So this read here on the other side has observed that create. So whatever read is going to do is going to go back in total order, correct? And observe the last write in that total order. And the last write to F1 is this one.
But is exists right?
No, exists is a read, but exist observe this particular write.
Oh, you're saying
You cannot read it back in time, correct? Like this is the whole goal.
right. But how did we know that it observed that exactly?
I told you that. I said like the file existed, so it must be the case that it observed it. The exist returned true.
But it existed before you deleted it, right?
Yeah. But you know, okay, well, go back in a second. Okay, so this is the second case. This is a good point. Let me talk about that. So like there's another scenario, and I think this is the one you're worrying about that could have happened. And this is where notifications come in. So Liz will agree that this is right, correct? So the second case, more rules. And this is indeed interesting. I think the case where you're worried about is, here's our reader again, here's our writer again, and the reader, you know, calls exists on ready. And let's assume the file, you know, is there, and you know, it does a read of F1. Right, so almost same as in the previous scenario. And now, like, you know, there's some change in leadership. You know, there's a crash, recovery, and all the kind of stuff is happening. And so there's a new primary. It deletes ready. You know, it writes F1. It writes F2. And it creates ready, like as before. And let's assume that this reader a little bit delayed. I don't know, something else happened on the machine, and you know, now it does the read of F2. And I think this is the question you're sort of asking about, because this seems worrisome, right? Because now there's a configuration change. And if this configuration change gets slotted in the middle here, correct, this read of F2 is going to return the new configuration as opposed to the read of F1 that is going to return the old configuration. And clearly things are going to be messed up. That is not a scenario we want to be in. So that would be a terrible outcome. And how does that actually, you know, get rectified, or how does actually Zookeeper deal with this? Well, this is where the watchers come in. You know, the picture that I drew in the previous board is not completely correct. You know, in addition to calling exist with this ready, it's going to say watch to true. And what that means is that this delete, you know, will change the ready file, and we have now set a watch on the ready file. And so when the ready file gets deleted, you know, by this new primary, that actually results in a notification. And there's a rule for this notification. And the rule for the notification is that every notification will be delivered for, you know, writes that go after it. And so what it has to be the case that, you know, this notification will be delivered before the write to F1. So there's two possible scenarios, correct? The notification gets delivered here, or the notification gets delivered like after the read of F2. Well, let me move that read of F2 slightly up. Or yeah. So it's still happening sort of in time behind, you know, the write operation. But the notification gets either delivered here, depending on the delays, or it's going to deliver to here. So
sorry, what's the exact wording of that rule that allows this to happen?
Basically, I think one way to think about it, a notification is like it's almost like a write operation, and the followers, you know, implement it so that if a change happens to delete, the notification goes off. That notification is delivered to the client with that ZXID. Again, the paper's not.
But I still don't understand why this guarantees that it can go like before. Wait, so the valid places for it to be are before the write of F1 and also like after the write of F2, right?
The notification is delivered after the delete of ready, and before the writes of F1 and F2 are visible, and the create, for that matter.
Oh, I see.
That's just a rule. Zookeeper has to guarantee that.
Okay.
Okay, so that means there's two cases, correct? Like the notification gets delivered before the read of F1 or after the read of F1. If it gets delivered after the read of F1 of F2, is there a problem?
No.
No, because then the read just happened before the writes.
Yeah, so everything is good. So this is if this whole block is happening after the read of F2 is perfectly fine. And how about here?
Wait, Professor, did you say the watch is like write something?
No, well, you can think about it. The watch is not a write operation. Yeah, I didn't mean to imply that, but the watch is executed with the appropriate sort of ZXID that's associated with that modification.
But those are local, right? The watches are.
The watches are local, and so when they're executed, it's guaranteed, that they happen at the write. When the write is observed, or the client sees that CXID, the watch is propagated with the CXID to the client and make sure that they're executed.
Thanks.
Again, the papers are slightly vague on exactly how it's implemented, but you can imagine different scenarios. But the more important point is like this rule is guaranteed. Okay, so what happens if the notification is delivered here? So the client is running, correct? Doesn't exist, the read F1, and now this notification comes in.
Then you have to restart, probably.
Yeah, you have to restart. Okay. So what we see here basically is that the rules make programming definitely a little bit more difficult, but not impossible. Right? With a little bit of careful sort of programming, you and understanding the rules, you can actually get the desirable results that probably the application wants.
What happens to read F1 though? What happens to read F1?
Well, you can start all over.
Oh, including that.
All right. Okay. And you'll see this is a trick that shows up in those recipes quite a bit, right? Like this idea of actually, bailing out and starting over again. Okay, good. So hopefully that gives you a sense that, for two things, there's sort of even though, one reason like people like linearizability is because it's very intuitive, very easy to program with because everything behaves like a single machine. But, if you want fault tolerance, scalability, it's hard to get actually good performance. And so one way to get good performance is to compromise on the consistency guarantee. And in this case, compromise on linearizability and provide some other consistent guarantee. And as we can see, that's it complicates, the user experience or the programmer experience. But these rules in Zookeeper are carefully chosen, so that still, things can actually work out, and it's doable. So it is possible to get the right, sort of guarantees. So now there's another aspect to this programming model that I want to talk a little bit about now that is really related to the coordination service part. And so the examples, that you need to, what does it mean to be a coordination service? One good example is probably the VM, the virtual machine fault tolerance paper from a little while ago that we read, and that had this test and set operation. Right, and the goal of the test and set operation was basically to make sure that there's no split brain, because basically two clients would run, and one would win the test and set and the other one wouldn't. And as a result, the one who won the test and set could conclude, that that's going to be the primary. And so that is sort of an example of a feature that a coordination service should be able to provide. And I want to, just to make that a little bit more concrete, let's think about like what lab 3, could you get that with lab 3? You can basically sort of get this a test and set type thing. Well, so let's do a very simple case. Let's say we have, here's our simple implementation of test and set. And in lab 3, we only have put and get operations, right? There's no other operations. So those are the 2 operations. So like, how might you write this? Maybe, we'll do a put, to a key, let's say master. And we put my IP address in it, the IP address of the caller. And then, we do a get, and we say if the get on master is equal to my IP address, then act as master or act as leader. So this is our naive implementation. We don't have many other choices because we only have to put we only have a put and a get, and this is how we're going to implement this. Will this do the desirable thing?
There's no atomicity between the put and the get, so maybe someone else changed it.
Correct. So basically, there could be 2 clients, correct? They both could execute the both puts at the same time, and then observe, roughly they do it at the same time, and they interleave, correctly, and both will actually return get, with their particular IP address, correct? And so we can get 2 leaders. And that's, of course, not what we want. So the main point of this example is there's basically, if you just have put and get, it's going to be very hard to actually implement a test and set. It turns out it's possible, but it's very complex. Use Baker's algorithm, you can basically probably do it, but like, it'd be ridiculous to do that in a distributed system. And so what Zookeeper does, it just provides some additional help to build these sort of type of primitives. And we'll see in a second. The other thing that, presumably what you want to know, and that lab 3 does not provide any support for, if you're sort of a configuration service or a coordination service, is that you want to know when somebody goes down. And for example, you want to observe that, like, if the leader goes down, like, somebody, the other parties would like to know, like, is the leader down, so that you can choose a new one if you needed to. And so, at least on the applications, the building using that service. Okay, so there's 2 things that we really want. One is, we want sort of way of trying to get this atomicity. That's what we're looking for in the Zookeeper design. And then in the Zookeeper design, the second thing we're looking for in the Zookeeper design is for an application to learn whether some node goes down. And so let's look at the Zookeeper API, and really, what we want to look at is the znode API. And you'll see again that it's actually carefully designed to actually make it possible to do the things that we're looking for. Okay, so the way the system is organized is, there's a tree of znodes. Typically, there's like one, sort of F1 has a znode that might have some children that correspond to the machines that are part, of F1. So maybe like peer or machine 1. Machine 2, like maybe the RP addresses or DNS names, machine 3, and they might actually have version numbers associated, or sequence numbers with them. And basically, these znodes can be of 3 types. One, they can be regular, so then they're fault tolerant, replicated, and all that kind of stuff. And then they can be ephemeral. And ephemeral basically means that the node will disappear automatically when the session with that with machine 3 goes away. So either because there's a network petition, there's no heartbeats more coming in from machine 3, but at some point Zookeeper decides that session is gone, and so then it will delete that node automatically. And so that's for ephemeral nodes. And then there's a third one, which is the sequential. Oops, let me go back to. And the third one, the type of nodes are sequential nodes, and that really means that they have a version number associated with them in their name, and they're created one by one under the particular Z node. All the children will have a sequence number in their name, and the nodes are not ordered by that sequence number. And so, for example, this might have sequence number 1, this might have sequence number 2, and this might have sequence number 3. And if a new one gets created, it will have a sequence number higher than 3. Okay, and then there's an API associated with that I want to talk a little bit about. There's create, which we already mentioned a little bit. It takes a path, it takes some data and flags, and the flags correspond, to the 3 cases. And then there's delete. And in the previous slide, that was a little bit misleading. Delete takes a path as before, but it also takes a version number. And exists takes a path and a watch. And then there's a get data primitive that takes a path and a version number. And we'll see that these version numbers are the trick, or the key to actually get our atomicity. And then there's set data, path, data, and a version number. And there's also a call for get children to get actually all the children of a particular Z node, which takes a path and I think a watch. And their sync, basically are sort of a cop-out operation to actually ensure that everything, so that if you really need strong linearizability. Okay. So I want to sort of talk a little bit about why this version number is handy. And so let's look at a particular example, the simplest example I can come up with, which is basically implementing a counter. And so the way you would write the if you write okay, so let me actually first give the right solution. So while true. The way you implement increment, so this is the pseudocode for increment of this counter, is you get x v get data of the counter, get data count, and then if set data count. Oops. So it's x plus 1 and the version number. And if that is the case, then break. Okay, so let me quickly go over this. So the get data returns the current version number and the value of the key. So the key or the path, so for the file count, it returns the value and its version number at that particular point when they did the read. And then you call and set data takes 3 arguments, the path, you can update the new value. In this case, it's going to be x plus 1 because we want to increment, the value by 1. And it actually passes in also the version number. And the semantics of set data is that if, the version numbers are still the same, then the set data actually happens and otherwise not. And so what does this protect against?
This prevents you from interleaving the get and set, basically.
Yeah. So if two two clients did get at the same time, they would read. They do get at the same time. They get both back, say, whatever, x is 0 and version number is 0. X is 0, version number is 0. Then they do both a put, where in this case is set data. So they set data with whatever x is 1, version number 0. Also, this guy does the same thing. Set 1 0. And why? And so both clients issue those two set operations. Are both set operations going to succeed?
Well, no,
And yeah, why not?
because one of the version numbers will be wrong.
Yeah, right. Like, so one of the two goes first. Why does one of the two go first?
Because all writes are linearizable.
Yeah, all writes are linearizable, so they go in some total order. So we can pick one. So let's say this guy goes first, or this operation goes first. So that will increase the value, correct, to the 1 from 0 to 1 as correctly, but that will also and will execute because the version numbers match, right? Like the version number 0 is actually what the current version number is, and so the version numbers match. The increment happens, and the set data returns true. And what will happen with the second one? Well, the second one, the version numbers won't match because the version number will be increased because this previous set data operation, and therefore the second set operation will fail. And so then the client will loop back and try again and try to take another shot and do the increment. And correct. So what happens in this case is correct. Even though the two clients executed the operation, concurrently, if the interleaving is bad, this piece of code will actually do the right thing. The second client will try again, and as a result, the end value will be 2 as opposed to 1. Okay. Does that make sense? If you've done any sort of lock-free programming in the past, then this might all look very familiar to you. And so this sort of a style of lock-free, basically Zookeeper sort of encourages this sort of style of lock-free programming. Okay. What I'd like to do, since I'm almost running out of time, and the last time I ran over time, is I'll want to talk at some point about locks, but I will do that next time, the next lecture. Now let me just sort of summarize what we've learned so far, and then I'll talk a little bit more about Zookeeper in the next lecture. So, summary. So basically, this is a very successful design. Oops. Widely used. You can download it. It's on GitHub. You can play around with it if you wanted to. And one of the things that is interesting about it, compared to all the systems that we've looked so far, it has weaker consistency. Which with weaker consistency, I mean it doesn't provide linearizability. And we've seen that basically as sort of a careful designed API, at least we have seen some aspects of the careful designed API that despite the fact that actually has weaker consistency, you can still use it. And in fact, you can use it actually for pretty important applications. You can actually use Zookeeper as a configuration service. So that's like it's its main purpose, sort of keeping track of like who's primary, who's in the what is the set of replicas, et cetera, et cetera. And so for this sort of crucial operation of being a configuration server, that has to be correct, because otherwise, we get this split brain problem. The API is carefully designed so that if you use the API correctly, you still can implement this crucial application on top of it, despite the fact that it actually provides weaker consistency. And the cool part of that is that this combination, of like sort of carefully designed API and the weaker consistency allows us to get, Zookeeper really high performance. And we'll see later in later lectures more of like this sort of trick of trying to weaken the consistency guarantees to actually either get better performance or be able to continue despite network partitions. Okay, let me stop here, and then I'll resume in a little while, and the next time around that we're lecturing. Any questions? Or, and again, as usual, if you have to go, please feel free to go. If you want to hang around and ask for more questions, please feel free to do so.
Sorry, can you go to this slide which said the set the unsuccessful example for this set and for the testing set. I think it's 2 slides back.
This one.
Yeah. So the new design, it is able to fix that, right?
Yeah, but you mean like with the APIs that Zookeeper provides?
The version, right?
Yeah, if you have no, so exactly. So I didn't get to do that, but that was the point of the rest of the lecture, is to talk about like how you can implement test and set using the version numbers. And clearly, the increment suggests you can, correct? Because this is basically the same sequence.
Right. Oh, right. If this is the same thing as the master. Okay, yeah, I see.
Yeah, exactly.
Okay. Thank you so much.
You're welcome.
I have a question about this versioning to prevent to implement lock-free programming. Is this like much more efficient than lock-free programming? Because you still need to like retry the operation again and again until it succeeds, right?
Yeah, like if test and set had a similar property, correct? If the test and set failed and you wanted to become, actual increment, you have to do that again. So it's often the case in this lock-free style programming that you can have these loops where you retry. And so if there's a lot of contention, you're going to get a lot of retry. Of course, if there's no contention, there's no retry. And typically, these lock-free algorithms actually are pretty careful in how they do the backup. So they don't really retry immediately. They have some backup plan.
Right, but what benefits does this give over a standard lock? Because either way, if you have a lot of contention, you're going to be like sitting there and retrying a lot.
Yeah. So let's the increment counter is an example where basically you sort of implicitly do the locking, because you will see if we implement locks in Zookeeper, like using the Zookeeper. Okay, if you implement locks with the Zookeeper API, and then if you do the stupid lock, you're going to also have this contention issue. Of course, there's a way of implementing the smarter lock that they talked about, like without the herding, and then you can do better. And so I was hoping to talk about that next time.
Okay, thank you.
I think the real point here is, that you can use these primitives to actually do lock-free programming. Like with the interface that the lab3 provides, it's not possible.
Makes sense. Thank you.
Any further questions?